Hi guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges, so anyone can watch my classes, and my classes are going to help the students to crack the examinations related to physical science. Okay, so well, guys, this is the lecture number 12 of quantum mechanics. So, unfortunately, I was taking 11th lecture. While taking 11th lecture, uh, my class was ended automatically because of technical error, right? So, now this is the lecture number 12 of quantum mechanics, and I'm going to start with probability current density, which I started in last lecture, but class was ended that time. Okay, so let's start. So we were studying step potential, okay? Step potential, step potential. Okay, so now we are going to study probability current density. Probability current density. Okay. Well, let me just check whether am I audible or not. Okay. But class was ended. Yeah, I am audible. So let's start. So So as we know, equation of continuity, right? Divergence of J plus del rho upon del T is equal to 0. This is called equation of continuity, and or we can say this flow of charges. Flow of charges. Equation for flow of charges. Okay, flow of charge or flow of charges. Okay. So similarly, and from here we can write divergence of J equal to minus del rho upon del T, right? And this is called diverging current density. Diverging current density. Diverging current density, and this is called decreasing charge density. Decreasing charge density, right? So this is current density is diverging, and charge density, that is decreasing, right? In similar way, we can write in quantum mechanics divergence of S plus del P upon del T equal to 0. Okay, this equation is called flow of particle. Okay, flow of particle, or we can say flow of probability. Okay, flow of probability. Okay, here S is called probability current density, and P is okay, and P is probability density. Probability density, or we can say probability of finding particle, right? Density. probability density. Probability density. Okay, this is the this is equation of, this equation is for flow of particle or flow of probability, where S is the probability current density, and which is very important. Okay, which we are going to use in step potential. Okay, so P is probability density. Okay, so from this we can also say, and also the value of S is, this is very important, S is minus I h cut upon 2m, minus I h cut upon 2m psi star gradient of psi minus psi gradient of psi star. Okay, this is very important formula. This is the probability current density. Okay, I will solve question, okay, where you will use this formula. Okay, and that question was asked in NET. Okay, so this is S equal to minus I h cut upon 2m psi star divergence of psi, sorry, gradient of psi minus psi gradient of psi star. Okay, so this is the formula for probability current density, very important formula. Okay, well, next is, so from here, from this equation we can say like this, del P upon del T equal to divergence of S, right? And now we can integrate it, and so this is going to be del over del T P dV equal to divergence of S dV, right? We'll solve it, and P is, where P is probability density, that is psi xt, which is function of psi xt mod square, right? So this we can write, this is del over del T integration psi, which is function of xt mod square dV, and this is, will use divergence theorem, so this is going to be this is minus. Okay, so minus minus S dA by using divergence theorem. Okay, and this value is P, so this is del P over del T equal to minus integration S dA. Okay, so from here we can write, integration S dot dA equal to minus del P over del T, right? From this, so what it is saying, what this equation is saying, this equation is saying that decrease in probability, decrease in probability, decrease in probability of finding particle, finding particle inside closed surface, right? This closed surface, use divergence theorem, right? So this is this statement say, this expression says the decrease in so we can see there is a decrease in probability of finding particle inside closed surface. Okay, from this. Okay, so well, now for all space, integration S dot dA is going to be 0, right? Surface integration S dot dA. So this means P del P upon del T is going to be 0. Okay, this implies P equal to constant. Okay, Next, I'll write very important note, okay, which is very important. You need to memorize it because we are discussing step potential, right? So this is this one for complex wave function for complex wave function, psi is going to be a e to the power iota kx. Okay, this is for complex wave function. Okay, this is for complex wave function, which is for example, this is complex wave function, right? Iota is here. So for this s, that is probability current density, is the formula for probability current density. S is, guys, please watch my previous lecture where I was discussing step potential. Okay, but in between class was ended because of technical error. So this is the second class wherein I started with with probability current density. When I was explaining probability current density in last lecture, that time class was automatically ended. So for understanding step potential, I would request you please watch my previous lecture. Then you will be able to understand. Okay. So S is for this S, that is probability current density, is the formula is h cut k upon m mod a square. Okay. And for real wave function, for example, okay, for real wave function, S is going to be 0. Okay, if there is a real wave function, for example, psi equal to a e to the power alpha x. Okay, so this is, there is no iota term, right? Alpha x. So this is real wave function. So very important formula for complex wave function. S is going to be probability current density formula is h cut k upon m mod a square. Okay, if this is the wave function. For real wave function, if this is the wave function, then S is going to be 0. That is probability current density. Okay, very important. Now using this, we are going to discuss step potential further. Okay, so psi in step potential, which I have already discussed, right? Psi in this incident wave function is a e to the power iota kx. Okay, which I have already explained in my last lecture, guys. I would request you please watch that class to understand this. Okay, and this is psi reflection. Psi reflection. The reflection wave function is b to the power minus iota kx, and psi transmission is, which we have studied, d e to the power minus alpha x. Okay, well, so this is the incident wave, this is the reflected wave, this is the transmitted wave, which I have already explained in my previous lecture. Okay, so from here we will find Si. Okay, S incident. Okay, S incident is going to be from this formula, right? That is because this the wave function is a e to the power I kx, right? So it is going to be h cut k, similar like this. Okay, h cut k upon m mod a square. Okay, for this wave function, because this is the complex wave function. Now psi reflection, sorry, SR, that is SR is reflected probability current density. is h cut upon k, h cut k upon m, h cut k upon m mod b square, right? This one mod b square from this, and st is going to be, that is transmitted probability current density, and that is going to be 0 because there is a real wave function, right? This is real wave function, there is no iota term. Okay, so this is going to be 0. Okay, next. Well, let me just check the internet connection. Okay, so next is now value of R, that is reflection and reflection coefficient and transmission coefficient, right? Which I have explained in earlier class. Okay, this is the one. Right. So R is the value of R in terms of probability current density. What is the value of that? Is R is reflection coefficient, right? Which I have already explained in my previous lecture. So this is reflected probability current density, probability current density, reflected probability current density upon incident probability incident probability current density. Okay, incident probability current density. So value of R is reflected probability current density is SR upon incident probability current density is SI. Okay, this is very important formula. The formula for reflection coefficient in terms of probability current density. Okay, and similarly, T is going to be ST upon SI, right? That is transmitted probability current density upon incident probability current density, and ST we have seen this is 0 for this wave function, right? Because that's a real function, so it is going to be 0. So earlier I have explained this R plus T equal to 1, right? This I have explained. So this means T is going to be 0, so R plus 0 is going to be 1, or we can say R is going to be 1, or value of R we have already found, that is value of R is mod B square upon mod A square equal to 1. Very important. Okay, mod B square upon mod A square equal to 1. Well, so this is the one. Okay, very important formula, this R, this one. Okay, mod of B square upon mod A square equal to 1. For this is the case first, guys, when V is greater than energy E. Okay, which for that you need to check my previous class. Okay, next point. Okay, so and now I'll explain like this, right? Now in quantum mechanics, for this, right? So this is step potential. This I have explained in a previous lecture, right? And this is V naught, and this is the energy. This is energy E. okay, and wave is coming like this because there is a oscillation, right? Oscillation, and here it is going to be like this simple because energy is less than r, and it's a real wave function, so this is just this wave, right? This one. So in cm, okay, this is one. Okay, in classical mechanics we know if E is, this I have already made, right? This in cm classical mechanics, if uh, E less than V naught, if E is less than V naught, this is the case, right? Less than V naught, okay. This means particle will never enter the region 2. This is region 1 and the region 2. Why? Because E is less than V naught, right? This is potential barrier actually, this one, right? Step potential. So, particle in classical, according to classical mechanics, what will happen? Particle will never enter in the region in region second, okay. But in quantum mechanics, there is a probability of finding particle in second region, okay. So there is probability of finding particle in the second region, okay. Probability of finding particle in the second region, okay. There will be some probability of finding particle in the second region according to classical mechanics, right? And so, and that p second is going to be probability of finding particle in second region is going to be psi 2 x mod square, right? This we know. Or p second is going to be with this wave function we know, right? So this is mod d square e to the power minus 2 alpha x, right? 2 alpha x, this one. This is the probability of finding particle in second region. Quantum mechanically we can find particle in second region, right? But classically it's not possible. Okay, so now for boundary condition like this, this one, for x equal to 1 upon 2 alpha p second, probability of finding particle in second region is going to be mod d square upon e, right? Because we will put value here, okay. And similarly for x equal to 1 upon alpha, probability of finding particle in region second is going to be mod d square upon e square, okay, right? So this is the case 1 which I have discussed. For understanding this better, I would request you please watch my previous lecture. Okay, well, now we are going to discuss case second, okay, of step potential, okay. Case second, of step potential. Okay, step potential. Case second. Case second is if E is greater than V naught. Okay, this is the case. So I'll make a figure for it. Okay, in next page I'm going to make a figure. Well, okay, so this is the potential V naught. Okay, and energy line. Okay, so this is E. Okay, so here we can see energy is greater than, this is the case of energy is greater than V naught, and this is the region first and this is the region second, first step potential. Okay, which we have already defined, that is V equal to uh, or Vx equal to, that is 0 for uh, x less equal to 0, and V naught for wave is coming like that. Okay, and this is going like this. Okay, I'll make it okay, like this. Okay, why here we can see this is a potential barrier, right? And so the wavelength is increased here. This is wavelength is lambda dash, here lambda, right? So wavelength is increases because it is going in higher potential region, right? So so energy will decrease, so energy of particle will decrease, that is wavelength of wave will increase. Okay, or k will decrease here. So here k is, that is wave vector is k dash, and here wave vector is k. Okay, this is the case, and we can see from here we can see k is greater than k dash, right? So again we'll write the Schrodinger equation for region 1. Okay, for region 1 Schrodinger equation. So we know Schrodinger's time independent equation, right? S I T E, right? We know that is del square psi upon del x square, or d square psi upon dx square, plus 2m upon h cut square E minus V psi equal to 0, right? This is d psi upon dx square. Okay, Schrodinger time independent equation. So we'll write here for region 1, the Schrodinger time equation is going to be This is going to be this one. This is going to be, just wait guys, my system got hanged. I would request you to wait, okay? Just give me 1 minute guys, okay? There is some issue. So I would request you, just give me 34 seconds. Okay guys. It's working now. So Schrodinger equation is going to be for region 1, for region 1, Schrodinger equation is going to be d2 psi psi 2, sorry, for psi 1, d2 psi 1 plus 2m upon h cut square e minus v psi is going to be 0, right? And for region 2, Schrodinger equation is going to be it is going to be d2 psi 2 upon dx2 plus 2m upon h cut square. This is v equal to 0 for region 1, right? So e psi equal to 0, right? And for this is going to be e minus v naught psi equal to 0, right? So, and for second, the solution is going to be, which I have already explained, psi 2 is going to be c e to the power c e to the power iota k dash x plus d e to the power minus iota k dash x, okay? So k dash is the wave vector for transmitted wave, right? So this is going to be now, and we know in the second region, in the second region there is no reflection. Why? Because E is greater than V naught, right? So in that case, D, this transmitted part is going to be 0, that is D is going to be 0, right? Means D equal to 0. So wave function psi 2 in the wave function psi 2 is going to be C e to the power I k dash x. Okay, C e to the power iota k dash x. Psi 2. And now, and where k is root 2 me, I have already explained it, 2 me upon h cut square, and k dash is root 2 m e minus p naught upon h cut square. Okay, this I have already explained in my previous lecture. Well, this is the one, and then psi incident. Psi incident is here a e to the power iota kx, which I have already explained, right? And here also this is the one, right? For region 1, psi 1 is going to be wave function by solving it, which I have already explained. It is going to be a e to the power iota kx plus b e to the power minus iota kx, right? So this is it is incident wave function, reflected wave function, and this is transmitted wave function. Okay, because there is no reflection in transmitted wave function. Okay, so psi incident is this, psi reflected is going to be b e to the power minus iota kx. Okay, and psi transmitted is going to be c e to the power iota k dash x. Okay, because the k dash is wave vector which is less than k, because the wave is going in higher potential. Okay, well, so this is one, and where k and k dash value I have already written. So now we can write SI, that is incident probability current density, that is going to be h cut k upon m. I have already explained it as well in my class, in previous class. Okay, and similarly psi r is going to be h cut k upon m mod b square, right? Because these are the values and we know how to get s. And similarly st is going to be h cut k dash, because in the wave vector is k dash in region second upon m mod c square. Okay, so now we'll find the reflection coefficient, which we know that is mod b square upon a square. I have explained in my previous lecture in detail. Okay, this one. So, and since we know k is greater than k dash, right? So r is going to be r also we know, right, in terms of probability current density, SR upon SI, right? So we can write h cut k upon m into mod b square, right? And upon a square value is h cut k upon m mod a square, right? This will get cancelled, so this will give mod b square upon a square, which is this, right? Similarly, transmission coefficient is going to be st upon si, transmitted probability current density upon incident probability current density. So this is going to be h cut k dash upon m upon h cut k upon m, okay, and this is going to be mod c square upon mod a square, right? H cut m will get cancelled, and this value is going to give this value is going to be k dash upon k mod c square upon mod a square, okay. Okay, well, next, now we'll use boundary condition. Now using boundary condition, okay. Boundary condition is also explained by me in previous class. Condition, boundary condition. So boundary condition is going to be, we know that is we know psi 1 equal to psi 2 at x equal to 0 at x equal to 0, right? Second boundary condition, we can write d psi 1 upon dx at x equal to 0 is going to be equal to d psi 2 region, right? Psi 2 upon dx at x equal to 0, right? This boundary condition also explained by me in previous lecture. Okay, so now we'll put the value psi 1 and psi a. This value we know, so psi 1 a e to the power I kx plus b e to the power minus I kx equal to c e to the power iota k dash x, okay. So at x equal to 0 and at x equal to 0, okay. So here we'll put x equal to 0, so it is going to be a plus b equal to c, okay. Equation number 1. Next is, so from now for second boundary condition we'll use, so we'll differentiate the psi 1 with respect to x, right? So it is going to be aik minus bik, okay. This is going to be del upon del x a e to the power iota kx plus b e to psi 1 value, okay, b e to the power minus iota kx at x equal to 0 is going to be del upon del x c e to the power iota k dash x, right? And now we'll differentiate and put x equal to 0, so it is going to be iota k a minus iota k b e to the power 0 is going to be 0 1, okay, and this is going to be equal to, this is going to be iota k dash c, right? Iota k dash c. So from here it is going to be iota k is going to get cancelled, so ab equal to c, no, I will get cancelled, ab equal to, this is k common here and here k dash, right? So this is going to be now, the value of C is going to be K upon K dash A minus B. Okay, this is equation number 3, and this is equation number 1, and this is equation number 3, equation number 2. Okay, so now we will solve equation 1 and 2. From 2 we'll put value in equation 1. Okay, so from 1 and 2, okay, this is okay, from 1 and 2, we can get A plus B is going to be, value is K dash A minus B, right? From there, the value of B upon A is going to be K minus K dash upon K plus K dash. Okay, very simple calculation. So then R is, we know, B upon A mod square, right? So this is going to be K minus K dash upon K plus K dash mod square. This is the reflection coefficient if energy is greater than V naught, step potential. Okay, and similarly we'll get transmission, that is mod C square upon mod A square. So we'll solve again equation 1 and 2, and that is going to give the value 4k k dash upon so I will solve it for you as well. So this one, how? Very simple calculation, better to solve. Okay, so like we have A plus, from equation 1, A plus B equal to C, or we have A minus B equal to this is K dash upon C, right? This equation number 2 and equation number 1, this one and 2 will be there. So we will add this, and then this is going to be 2A is going to be, value of A is going to be 2A is going to be C into K dash upon K plus 1. Okay, so then the value of A is going to, value of C is also here, right? Value of C upon A is going to be 2K upon K dash plus K. Okay, so now we will find R. R is going to be K dash upon K and mod C upon A whole square. Okay, because here R is there, I have also explained that R. Okay, so this one, so this one, right? So now we'll put the value, sorry, T, this is T, not R. This is T. Okay, so then T is going to be, we'll solve it, this is K upon K dash upon K into here this case is different, right? So this is going to be 2K upon K dash plus K whole square. Okay, so this value is going to give 4K K dash upon K dash plus K whole square. Okay, this is the transmission coefficient and this is the reflection coefficient for the second case. Okay, well, this is the one, and also you need to note that the value of K dash K is, value of K dash K is, if we put the value of K dash upon K, so this is going to be root 1 minus V naught upon E. Okay, V naught upon E. E is greater than V naught. Okay, okay, so 1 minus V naught upon E, this is the value. So in terms of this we can also find the value. So R is going to be R is going to be like we know our value of R is K minus K dash upon K plus K dash whole square, right? This we know. So in terms of and we know the value of K K dash K, right? This we know, this is root 1 minus V naught upon E. Okay, this one. Now we will put the value. So this also we can write R, we can also write in terms of like this 1 minus K dash upon K by dividing K, right? Whole square upon 1 plus K dash upon K whole square. Okay, and if you put the value, so this is going to be 1 minus root 1 minus V naught upon E upon 1 plus root 1 minus V naught upon E whole square. Okay. Similarly, T, if you put K dash upon K equal to 1 minus V naught upon E, so that is going to be 4 root 1 minus V naught upon E upon 1 plus root 1 minus V naught upon E. Okay. So these are the deflection and transmission coefficient for the case 2. Okay. So step potential is completed, guys. So there are 2 lectures of step potential in which I have discussed all 2 cases for step potential. In next lecture we will discuss some questions related to step potential. Okay. So well, thank you so much for watching my lecture, guys, and also I would request the people who haven't subscribed my channel yet, please subscribe my channel and watch my lectures free of charges. Okay, and my lectures are going to help you to crack the examinations related to physical science. Okay, okay guys, thank you so much. Bye now.